Hello learners. So previously we have studied how we compute the page rank on a graph and how the links are used for analyzing the web structure and how the MapReduce has been used to compute the page rank scores. Then we have studied about the hubs and authorities, how they are used to compute the importance score of a page rank. Then there are other issues that are associated with the page ranking. We have studied that for computing the page rank iteratively, say Rj is representing the page rank of a jth page as t plus 1 iteration, which is the summation of Ri divided by Dj, where I is pointing to j and Dj is the outgoing links from jth page. RIT is the tth iteration, or we can write it in the R is equal to M into R, where M is the adjacency matrix that we have learned. Now question arises, does this converge? We have seen previously using an example that we can converge the page rank when the difference between the t plus 1th iteration and the tth iterations remains less than epsilon. So, but the question is, does this converge? Does it converge to what we want? And are the results that we are receiving are reasonable? First consider whether the page rank converge or not. For example, let's consider a web graph of two nodes where each node is pointing to each other. That means A is pointing to B and B is pointing to A. So using the formula Rj is equal to summation of Ri divided by Dj, where I is pointing to j, we first initialize the vector R at time 0 to have two values, value 1 on the node A and value 0 on the node B. So the adjacency matrix of this graph would be M is equal to 0, 1 and 1, 0. Multiplying the n times R, then following is the outcome. Say at first iteration, when we use this matrix 0, 1 and 1, 0 row wise and multiplying this with the R0 value, which is 1 initially at A and 0 at B, the results comes out to be 0, 1. That means now the value at RA becomes 0 and RB becomes 1. Then the second iteration R2, the value again flip 1, 0. A becomes 1 and B becomes 0. R3, 0, 1, value again flip, RA becomes 0 and RB becomes 1. And R4, again value flips, RA becomes 1 and RB becomes 0. So in the next time or in the next step, the value will again flip. And now when we multiply again, the value will flip again. Never converge, because the score of 1 get passed between A and B. We have initially considered that RA plus RB should be 1. Now as both are pointing to each other and there is no other links, so the score is get transferred from one to another. So A score of 0 get passed between B and A. Seems that page rank computation will never converge. So this is a problem and called the spider trap problem. Another example, does it converge to what we want? Say we have taken a topology of two nodes or a web graph of two web pages where page A is pointing to page B. So node A and node B and one edge. So here we start with score 1 and B starts with score 0. So adjacency matrix will be 0, 1, 0, 0 column wise, and when we are computing RA, RB, multiplying it with 1, 0, we are having 1, 0 at iteration 0. At iteration 1 we will be having the score 0, 1 and at iteration 2 we will be having the score 0, 0 and 0, 0 again 0, 0. So the first multiplication with matrix M, the score gets flipped In the second step of multiplication, basically the score 1 gets lost. Thus, A and B are not able to pass the score to anyone else. So, the score gets lost. And we converge to this vector of zeros, which is a problem called dead end problem. Here is the example showing this. There are 8 nodes or 8 web pages, or you can say it is a web graph of 8 web pages where 1, 2, 3, 4 are represented in red colors and 5 is representing with blue color. The 5 is receiving a link from 3 and thereafter there is no other link from page 5. So, this is a dead end. Some pages have no outlinks. Random walk has nowhere to go to. That means randomly you cannot go anywhere once you reach the page 5. Then such pages cause importance to leak out. Then 6, 7, 8 are represented using the green color. The page 6 is receiving an incoming links from the page 4, and then from 6 you are having a link to 7, then from 7 to 8 and then from 8 to 6. But 6 is having no outgoing links to the web graph that is shown in the red color. So, this is known as the spider trap. Once you reach to the page 6, you will be getting the trap between the pages 6, 7 and 8. So, this is an endless loop, so known as spider trap. All outgoing links are within the group. So, random walk gets stuck in a trap and eventually spider traps absorbs all the importance. The importance will be communicated between these 3 web pages only, 6, 7 and 8. So, these are the 2 major problems. Now, again let us see using the topology of Yahoo, Amazon and Microsoft. Y is representing Yahoo, A is representing Amazon and M is representing Microsoft. So, the links Y to Y, Y to A to Y and A to M. And then we are representing this structure, this links using the adjacency matrix of YAM as row wise and YAM as column wise. I am reading this matrix column wise. So, from Y we are having link to Y 1 by 2, Y to A 1 by 2, Y to M there is no link 0. Again the second column, link from node A to Y is 1 by 2, A to A there is no link 0, A to M there is a link 1 by 2. Then link from third column M to Y there is no link 0, M to A 0, M to M 1. So, we are having a spider trap at M. Once you reach M, you will having an outgoing link only to M. So, this is a spider trap. Writing the equations for page rank, Ry is equal to Ry by 2 plus Ra by 2. Ra is having only one incoming link, Ry by 2, Rm is having 2 incoming links, Ra by 2 plus Rm. Let us say initially we are having that by a random walk we can reach to any page. So, initial page rank is 1 by 3, 1 by 3 and 1 by 3 for all 3, and then multiplying with the adjacency matrix we will be having 2 by 6, 1 by 6 and 3 by 6. I am showing this computation here. In the adjacency matrix 1 by 2, reading it row wise 1 by 2 and 0, multiplying this first row with the column 1 by 3, 1 by 3 and 1 by 3 and receive the value as 2 by 6 because 1 by 6 plus 1 by 6. Then the second row 1 by 2, 0 and 0 multiplying with the matrix 1 by 3, 1 by 3 and 1 by 3 will receive 1 by 6. Then 0, 1 by 2 and 1 multiplying with 1 by 3 will receive 3 by 6, and this is the result shown in the second iteration result. Then using this iteration result as the input for the another iteration, we will receive first row multiplying with the matrix R1th iteration will receive 2 by 2 plus 1 by 2 comes out to be 3 by 12. Then 1 by 2 0 0 multiplying with 2 by 6 comes out to be 1 by 12. then 0, 1 by 2 and 1 multiplying by the our 1th result comes out to be 1 by 12 plus 3 by 6, which comes out to be 7 by 12 and shown here as the third iteration result, and so on. And at the last, by moving number of iterations again and again, we will reach to the final result as 0, 0 and 1. That means all the importance, all the PageRank scores will get merged at M, having the highest score. So this is a spider trap problem. Now what is the solution? So the solution of the spider trap is the teleports. Google solution for spider traps is teleporting. At each time steps, the random surfer has two options. With probability beta, it follow a link at random, and with probability 1 minus beta, it jump to some random page. And the common values for beta are in the range of 0.8 to 0.9. So surfer will teleport out of spider trap within few steps. And here in this diagram, left hand side, the initial web graph is now showing 3 green links, dotted arrows. That means there is a possibility that randomly from Y it can move to some another random page, from A it can move to some another random page, and from M it can move to some another random page, which is the probability of 1 minus beta. You must have seen while you must be surfing the web that you click on the web page, some hyperlink, but you move to some another new web page. This is the teleporting. Then let's consider the example of dead ends. M is a dead end. There is no link, outgoing link from the page M. The adjacency matrix is written similarly from Y to A, Y to M, 1 by 2, 1 by 2 and 0. The second column is link from A to Y is 1 by 2, A to A is 0, A to M is 1 by 2. And from M, as there is no outgoing links, so the column is all zeros. The PageRank equations for all three PageRanks will be Ry is equal to Ry by 2 plus Ra by 2. Ra is receiving one incoming link Ry by 2, and Rm is Ra by 2 plus Rm. So computing this by multiplying with the adjacency matrix, initially we considered that at random each page is having equally likely chances of occurring. So 1 by 3, 1 by 3 and 1 by 3. So multiplying this with the matrix, we get 2 by 6, 1 by 6 and 3 by 6. And then using this 2 by 6, 1 by 6 and 3 by 6, we get 3 by 12, 1 by 12 and 7 by 12 and so on. Multiplying the adjacency matrix 1 by 2, 1 by 2, 0, 1 by 2, 0, 0 and 0, 1 by 2, 0 with the initial chances of equally likely of these three pages, we get 2 by 6, 1 by 6 and 1 by 6 at the next iteration result, and multiplying the adjacency matrix using this next iteration result, we get 3 by 12, 2 by 12 and 1 by 12, so on, and at the end we will get all zeros, because while reaching the M where we are having no outgoing links, the importance score get lost. So what is the solution? Solution is always teleport. So teleport, follow random teleport links with probability 1.0 from dead ends. So and adjust the matrix accordingly. So initial matrix was having M as having no outgoing links. So the scores were 0, 0 and 0. But we have adjust the matrix that from M it is required that always random page should be followed. That means the link can go to Y, A and M with the equal probability 1. So we have distributed that one probability into 3 links, 3 nodes Y, A and M, which comes out to be 1 by 3, 1 by 3 and 1 by 3. This is an example how this random teleport solved the problem. So adjacency matrix is M 1 by 2, 1 by 2, 0, 1 by 2, 0, 0, 0, 1 by 2 and 1 with the probability 0.8, beta is taken 0.8, and the probability of 1 minus beta is to having a random page. Jump to the random page is 1 by 3, 1 by 3, 1 by 3, which is an identity matrix of 1 by 3. So A comes out to be the adjacency matrix. After multiplying this, we get 7 by 15, 7 by 15, 1 by 15, 7 by 15, 1 by 15, 1 by 15, 1 by 15, 7 by 15 and 13 by 15 respectively. So at the right hand side, 3 pages are shown in the red color, Y, A and M, and you can see that each one is having a self link. Y to Y is having a chances, A to A is having a chance, M to M is having a chance. The green arrows is showing the chances of 1 minus beta times you can move to a random walk, and black arrows are showing the initial link to that particular web pages. So the chances of having A to A is 1 by 15, chances of having M to M is 13 by 15, chances of having Y to Y is 7 by 15, chances of having Y to M is 1 by 15, chances of having M to Y is 1 by 15, chances of having M to A is 1 by 15. So these are the links that has been additionally added with probability of 1 minus beta. Here in this example, we have considered beta as 0.8. So starting with the first iteration, having the values 1 by 3, 1 by 3, 1 by 3. In the second iteration, we are having the values 0.33, 0.20 and 0.46, and so on. At the last, we are having 1 by 33, 5 by 33 and 21 by 33, which was initially 0 when we are having no options of teleporting. So always teleporting solves the problem of dead ends. Now how we use this beta probability of teleporting in computing the page rank. So we have taken R new is equal to A into R old, where A is beta times the adjacency matrix M, that is the initial matrix, and 1 minus beta time is 1 by nth matrix, which is the identity matrix containing the 1 by nth, and this is the n cross n matrix, where n are the pages that we are considering. So if there are n pages, we will be having 1 by n values containing matrix of n by n order. So consider page I with di outlinks. So Mij, that means the adjacency matrix, will be having the values 1 divided by di. If I having I is pointing to a page j, or 0 otherwise. So random teleport is equivalent to adding a teleport link from ith to every other page, setting transition probability to 1 minus beta divided by n, reducing the probability of following each outlink from 1 divided by di to beta divided by di. So text each page a fraction 1 minus beta of its score and redistribute evenly. This is known as taxation. That means we have added a text for following a page. So this has again changed the page rank equation. Initially we are having R is equal to M into R. Now we have converted this as R is equal to A into R, where Aij is equal to beta times Mji. That means beta with probability beta, the adjacency matrix will be followed, plus 1 minus beta time divided by n. Rj, then the second steps, again we are converting it to Rj is equal to summation of Aij into Ri, where I varies from 1 to n. There are n source pages. Rj is equal to, now we are replacing Aij with the values written in the first equation, beta Mij plus 1 minus beta divided by n multiplying by Ri. Again computing, again solving this. So we have taken out the summation of Ri outside. So summation of beta Mij into Ri plus 1 minus beta into n summation Ri. Since the summation of Ri is 1, it is a condition that the page rank scores of all the pages in a web should be equal to 1. So we have removed that summation. The remaining terms remains as summation of I from 1 to n beta times Mij into Ri plus 1 minus beta divided by n, which comes out to be finally page rank score R is equal to beta times m into R plus 1 minus beta divided by n, where n is the number of web pages. Now, how the complete page rank algorithm works? For that, we first take the graph G as input and the parameter beta. So, directed graph G can have spider traps and the dead ends that we have just discussed, and parameter beta is the probability by which we are following this. See, and the output will be the page rank vector R new. So, first of all, we will set the Rj old as 1 divided by n. Now, if the graph does not have any dead end, then the amount of leaked page rank is 1 minus beta. On the other hand, if there are dead ends, the amount of leaked page rank may be larger. This initial equation assumes that matrix M has no dead ends. That means the matrix M is followed using the probability beta. So repeat until converge. कब तक repeat करना है? Till you are having the difference greater than epsilon. So Rj new minus Rj old is greater than epsilon. Rj new is computed as summation of I pointing to j beta times Ri old divided by Di, where Di is the outgoing links or in degree of j is 0. Now reinsert the linked page rank. So Rj new is equal to Rj new plus 1 minus s divided by n, where s is equal to summation of R new j. R old is assigned the new value and this iteration will move on until Rj new minus Rj old is greater than epsilon. So it can either pre-process to remove all dead ends, or it has to explicitly follow random teleport links with probability 1 from dead ends. So the computation of new page rank is done repeatedly until the algorithm converges. So the algorithm has to explicitly account for dead ends by computing S. Sometimes we are not interested. The goal is to evaluate web page not just by the popularity but also by the relevance to a particular topic. For example, how much that particular page is relevant to sports or the history. So this is known as the personalized page rank. So search queries to be answered based on the interest of the user. For example, the search query Jaguar wants different pages depending on whether you are interested in automobiles, nature or sports. Might discover interest by browsing history or bookmarks. So in any case, the idea would be that you would like to compute different importance scores of different web pages based on their relevance to a given topic. So there comes the idea of teleport sets. The way to achieve this is by changing the random teleportation port. In the original page rank formulation, the random walker can land at any page with equal probability. In the personalized page rank, the random walker can teleport only to a topic or specific set of relevant pages. Whenever a random walker decides to jump, they do not jump to any page on the web, but they only jump to a small subset of pages, and this subset of pages is called teleport set. When the walker teleports, they can only teleport into a small set of pages. So consider S as the teleport set. The set S contains only pages that are relevant to a given page or that are relevant to a given topic. This allows us to measure the relevance of all the other web pages on the web with regard to this given set S. So for every set S, for every teleport set, you will now be able to compute a different page rank vector R that is specific to that data point. To achieve this, page rank formulation is changed as Aij is equal to beta times Mij plus 1 minus beta times divided by S, that is I belongs to S, where A is a stochastic matrix, I is the entry, S is the set, and 1 minus beta divided by the S is the random jump probability to a particular page belonging to set S. So this is that we can only teleport to a topic sensitive page rank, so known as the personalized page rank. So in this session we have studied how the page rank problems can be solved using the teleports. The problems like spider taps and the dead ends can be solved using the teleports, and how we can teleporting to a topic sensitive page using the teleport sets. So this is all. Thank you.